In the Synapse project, funded by the third dAIEDGE open call, we examined the collaboration of LLM and active inference policy-aware agents for the spatial web using the Wactorz platform. To this end, we used a 3-floor office building from the Synergym simulator, which wraps Energy Plus, and built a customized version on top of it, the digital twin you see in this video. Each floor is packaged as one HVAC air loop, with the 5 zones on a floor share one fan, one 2-speed cooling coil, and one outdoor air system for fresh air. That shared plant is the important detail. The zones are not independent. Because they draw on the same fan and coil, one agent's action changes the conditions its neighbors face. We treat this setup as partially observable, with one active inference agent in charge of each of the 15 zones. Each agent sees only what a real controller in that room would see: its own zone temperature, the outdoor temperature, solar radiation, humidity, time of day, and occupancy, represented by white circles. It does not see the full state of the building, and it does not see what the other agents are doing. From that limited view, each agent maintains a model of how its zone is likely to behave, predicts where it's heading, and acts to keep it comfortable for the least energy. Choosing the action it expects will least surprise its own model of a comfortable, efficient zone. It plans a few steps ahead rather than reacting to the current reading. Because each agent anticipates rather than reacts, the building stops behaving like 15 rooms fighting over the same supply. Conventional control has every zone respond to the same morning temperature drop at the same moment, so the whole building peaks together. Our active inference agents stagger, preconditioning when it's cheap, backing off when their neighbors are drawing. The result is an 8.5% lower peak than a conventional rule-based controller without giving up comfort, and peak demand is what a facility actually pays for. The environment is also decentralized. There's no central controller holding the whole building's state. Each agent is independent, so the approach scales. Adding a floor means adding agents, not retraining a monolith, and degrades gracefully. If one agent fails, 14 keep working. Everything in the building, every zone, agent, observation, and decision, lives in a shared knowledge graph built on open spatial web standards. We use HSML to model the building as something the system actually understands. A zone is a space is on a floor, an agent controls a zone. And every action carries its provenance: who did what, to what, and when, so nothing happens anonymously. That means you can ask the building questions in plain language and get answers grounded in fact. If the user asks, which agent controls core bottom area, the system provides the answer and shows the exact SPARQL query it ran to find it, following the provenance link to a verified answer. So when a manager asks why the building did something at 6 a.m., the answer isn't "the AI decided." It's a specific agent using its expected free energy, a specific trigger, and a query anyone can rerun to check. We used a Gemma 426 billion language model running on an NVIDIA DGX Spark to map the questions from natural language to SPARQL queries. Alongside the 15 controllers, we deployed a 16th agent, a forecast-based anomaly detector. We trained a model that predicts what each zone should do next given the current conditions and the action being taken. When reality diverges from that prediction, and keeps diverging, we flag it, accumulating the deviation over time rather than reacting to a single bad reading that could be due to an open door or window. Our detector caught the drift faults we injected with over 85% F1 score. All of these agents run on edge hardware, on-site. Because every part of this runs on-site, no occupancy data, no sensor readings, and no building behavior ever leaves the building, making the solution privacy-aware by design. The language model runs on an on-premise NVIDIA DGX Spark. The agents themselves, alongside the Wactorz platform, an MQTT broker, and a Fuseki server, run on a single Raspberry Pi 5, with the active inference agents planning concurrently in under 500 milliseconds per action, plus the anomaly detector. The users are able to see the resource utilization metrics in terms of CPU usage and memory using the Wactorz dashboard. Synapse project was also evaluated against a real-world scenario using the developed Home Assistant add-on of Wactorz, so stay tuned for more videos to come on integrating AI agents with IoT environments.